All right, hi everyone. Today we're going to be talking about measuring light and also calculating daily light integral in the greenhouse. And so as a bit of a refresher, you'll remember we've been talking a lot about light intensity, and specifically how when we're looking at plants in the greenhouse, we want to measure light as a particle, also known as quantum. What we're looking at is how many photons or packets of energy a plant has available to drive photosynthesis and growth. And so what we want to do is measure how many of these photons, again, our plant has available. The way that we measure that is what's referred to as light intensity. When we look at these photons, what we're interested in is actually a very specific range of wavelengths, also commonly referred to as the photosynthetically active radiation, or PAR. And so these photons are going to be anywhere from 400 to 700 nanometers in terms of length, and that corresponds to their color. So blue photons all the way up to the red photons. And so when we're measuring how many photons are available within this specific range, the term that will be used is photosynthetic photon flux density, or PPFD. And again, we're looking at how many micromoles of photons are available specifically within that PAR range to the plant every second. And so this is what's referred to as an instantaneous measurement. So to help you wrap your head around this concept, I really like this figure that you'll see here at the bottom right, where you see all these individual photons, and what we're measuring with PPFD is how many of these photons are hitting a square meter every single second, that are again within that wavelength range of 400 to 700 nanometers. And so we're measuring in moles or micromoles in this case, which you'll probably remember as a constant from chemistry. But again, the important thing to note right now is that this is an instantaneous measurement every second. Unfortunately for the greenhouse, that's not incredibly valuable. We don't really care about what light our plants are receiving at this specific second. We more so want to look at how much light did my plant actually accumulate over the course of the day. And so a more helpful metric that we'll often use is daily light integral, or DLI. I like to think about this as a rain gauge. And so we're basically looking at how many photons did I accumulate over the course of the entire day that my plant could use to drive photosynthesis. And so instead of micromoles, we're measuring in moles. Instead of seconds, we're looking at days. And so how many photons did I accumulate over the course of this entire day? So again, think about a rain gauge as a great comparison there. Now there's lots of tools we can use to measure light in the greenhouse, but we're commonly using quantum sensors, and those quantum sensors will measure that instantaneous light intensity, and many quantum sensors will then take that information and help you to calculate DLI, so how much light did you accumulate over the course of the entire day. So a lot of these systems can be automated. However, I think it's incredibly important for also for us to know how we can calculate some of these DLI as well as PPFD by hand, so that we can better understand some of the applications we may want to use in a greenhouse environment. And so that's what I want to work through next, is really looking at how can we convert between PPFD and DLI. And we do that by using this equation where we can see that DLI is going to be equal to our photosynthetic photon flux density times 60 seconds per minute times 60 minutes per hour times our operation hours. And so operation hours meaning how long are my lights on over the course of a 24-hour period. So that could be 12 hours, that could be 18 hours, however long those lights are on. And then I'm going to divide that by 1 million micromoles per mole. And so these are a bunch of conversions. There's 1 million micromoles in a mole, 60 minutes in an hour, 60 seconds in a minute. So you can see that we're just converting units to try to solve for what's our DLI, and again, or backwards, what's our instantaneous light intensity, or PPFD. Now, the best way I've found to wrap your head around this equation is just to put it into practice. And so I think what I would like to do next is for us to just work through a couple of example calculations of how we can use this equation and ultimately solve for DLI as well as PPFD. And so let's go ahead and look at our first question here, where in this case we have an HPS lamp and it's installed 8 feet above a bench of petunia plugs in a commercial greenhouse. Scans with our quantum sensor are going to reveal that the lamp is emitting an average light intensity of 70 micromoles per meter squared per second at canopy height. If that lamp is left on for 18 hours a day, what is its contribution to our daily light integral, or DLI? So what we can do is look at this equation, and you'll see that there are two unknowns in terms of solving for what the contribution to DLI is, because DLI is going to be equal to PPFD. We then have our conversion units of 60 seconds in a minute, 60 minutes in an hour, but then we also need to know how long are these lights on, which is our operation hours. So in this case, our ppfd, if we look up at this question, we can see that the light intensity that our lamps are emitting is 70 micromoles per meter squared per second. So that's what we would put in our ppfd blank that you see over here on the left. And then for the operation hours, we see that the lamps are going to be left on for 18 hours a day. And so that's what we would slot in for our operation hours. And so you can see here in this case that, again, simply put, I would just slot in 70 micromoles per meter squared per second, and I would slot in 18 hours per day. And using this then equation, I'd be able to solve for what is my final DLI. And so if we look, I went ahead and populated this equation with our correct answers that we pulled from that question so that then we can move through what are these remaining steps. And so in this case, first we just need to do some multiplication. And so if we take that 70 micromoles per meter squared per second, multiply it times 60 seconds in a minute, multiply that times 60 minutes in an hour, and then multiply that times 18 hours in a day, what we will find is that our answer here will be, we have 4,536,000 micromoles per meter squared per day. And so what we've just done is we've converted all of our units. We've gone from seconds to days, and we still are dealing with units in this case of micromoles. We have 4,536,000 micromoles per meter squared per day. But remember that we still have this ultimately being divided by 1 million micromoles per mole. And so in this case, what we can do is simply just divide. And the reason we do this is we're converting from micromoles to moles because moles is a way easier number to deal with. Instead of talking about 4 million micromoles, we can instead, in this case, what you're going to see is go ahead and just talk about a much easier to use metric. So in this case, our DLI would be equal to 4.536 moles per meter squared per day. And so all we're doing is, again, canceling out units, some simple division here to find that we have a manageable number now of our DLI contribution from those lamps is 4.536 moles per meter squared per day. Let's go ahead and look at another example, and we can just walk through this one together as well and go through it a little more quickly. So let's say in this example, we just installed new overhead LED supplemental lighting fixtures for our use in hydroponic cucumber production. So based on the scans that we collected with the quantum sensor, we find that our lamps are emitting an average light intensity of 190 micromoles per meter squared per second at canopy height. If those lamps are left on for 20 hours a day, what is our contribution to DLI? How much DLI, what is that DLI that our lamps specifically are going to be adding to our crop? And so in this case, we use that same equation and we can go ahead and start populating this information. So again, remember 190 micromoles in 20 hours a day. So in this case, our PFD is 190 micromoles per meter squared per second. Oops, I'm sorry. We're going to multiply that times 60 seconds in a minute. Multiply that times 60 minutes in an hour. And then we're going to multiply this finally, not by 24 hours in a day, but in this case, we said that our lamps are going to be on for 20 hours per day. So 20 hours per day. And again, remembering that we are going to divide all of this by 1 million micromoles per mole. So again, what we're doing here is converting these units to try to get from micromoles to moles and ultimately from seconds to days. And so if we go ahead, we can multiply across this top row. So we're going to take that 190 multiplied times 60 times 20. And what we're going to find is that we have 13,680,000 micromoles per meter squared per day. And again, what we want to do is ultimately convert that into moles, which is why we have 1 million micromoles per mole here on the bottom. And so now we can just divide that 13,680,000 micromoles by 1 million moles per mole, and that will give us our final DLI, which in this case is 13.68 moles per meter squared per day. So I hope you see this is a relatively easy, straightforward process of us being able to take information of how much light we're receiving from a lamp, and using how long we have those lamps on, convert into what's that contribution, in this case to DLI. What is that addition to DLI that I'm going to receive just from my electric lamps? Now, what's important to understand, though, is that these equations can actually work in both directions. And so let's look at another example to see how we could instead solve for what is the ppfd I need to achieve from my light source itself to achieve a target DLI. So in this case, let's say we're a plug producer and we're targeting a greenhouse DLI of 12 moles per meter squared per day in January. Our average solar DLI in the greenhouse during this time of the year is 8 moles. So our target is 12, solar DLI is 8. We have a difference here that we need to make up with supplemental lighting. So using a 16-hour photo period, what is the minimum ppfd emitted from supplemental lighting necessary to achieve this target DLI? So we can use this exact same equation, and in this case, instead of solving for DLI, we're actually going to be solving for ppfd. We want to know what is that instantaneous light intensity, that ppfd, that my lamps need to be providing so that I can achieve this target DLI. Now, what's a little confusing about this, let's go ahead and go to our next slide, and we can see where we need to start filling in information from our question. One of the first things I want you to notice that I have bolded here is that our target is 12 moles, but we're only receiving at this time of the year 8 moles. And so what we need to achieve from our supplemental lighting system is at least 4 moles per meter squared per day. So all I'm doing is saying if my target is 12 and I'm only getting 8 from sunlight, that means 12 minus 8, I need to make up that difference of 4 moles from my supplemental lighting. So we're going to solve for 4 moles here. We're trying to solve for ppfd, so we don't want to put anything in that position yet in the equation. But what you'll see is that we mentioned that we are going to use, in this case, a 16-hour photo period. So we can go ahead and put that into our equation here. 16 hours per day. That's how long we're going to have those lights on. So similar to our last question, I went ahead and populated our information in the equation up here above based on what we just wrote on that previous slide. So what we need to do in our first step is literally just do that multiplication again. And so what we're going to have here is we have 4 moles per meter squared per day is going to be equal to, in this case, our ppfd, which is what we're trying to solve for, multiplied times, ppfd multiplied times, in this case, 60 times 16. And so we can go ahead and do this multiplication now so that we can start working through the remainder of the question. And so in this case, 60 times 60 times 16, that is going to give us 57,600. And so what you're going to see that we need to do at this stage of the problem, and we've got our 1 million micromoles per mole here on the bottom. And so what we're going to need to do at this stage of the problem is cross multiply and divide, which again, probably something you are very familiar with. We're going to have to multiply both sides by 1 million, and then we're going to have to divide both sides by 57,600. So if we go ahead and multiply both sides by that million, what you're going to find is that if we look over here on the left side of the equation, we're going to end up with 4 million. Now we have micromoles per meter squared per day because we've converted those units, and that's going to be equal to ppfd times 57,600. And then what we're going to need to do is, again, divide both sides by 57,600. And so in this case, we're going to have ppfd is equal to 4 million divided by 57,600. And so what we find is that our target light intensity needs to be 69.4 micromoles per meter squared per second to achieve this target DLI that we're aiming for. So hopefully that makes sense. What you can see is that we can seriously move either side of this equation. If we need to solve for PPFD or if we need to solve for DLI, either of those can be solved for using the exact same equation. We just need to know which way we ultimately need to work that equation. Whoops, and so you see my arrow unfortunately populated there. I got a little bit ahead of myself moving through these steps. So let's go ahead and let's look at one more example problem to, again, show you how we can work this equation in reverse. And so let's go ahead and say in this case that we're a hydroponic tomato producer targeting a DLI of 30 moles in your greenhouse during December. The average solar DLI in the greenhouse during this time of the year is only 12 moles per meter squared per day. So if we were using an 18-hour photo period, what is the minimum PPFD emitted from supplemental lighting necessary to achieve this target DLI? So in this case, what we first want to start with is if we're achieving 30 moles from, if our target is 30 moles per meter squared per day, and our average solar DLI is only contributing 12 moles per meter squared per day, that leaves us with an 18 mole per meter squared per day deficit that we now need to make up. And so using this information of 18 moles and an 18-hour photo period, we can now solve for PPFD just like we did on the previous example. So let's go ahead, and I've got a nice white sheet that we can start working off of. And so in this case, we know that our target, which is a pretty high target, is going to be 18 moles per meter squared per day. That's what we want to achieve. And that's going to be equal to what we need to find, which is our PPFD multiplied times 60 seconds in a minute times 60 minutes in an hour times, in this case we said 18 hours in a day. So we have an 18-hour photo period, and all of that is going to be divided by 1 million micromoles per mole. So in this case, we can go ahead and multiply the top to start to simplify this down. So we're going to have 18 moles per meter squared per day is going to be equal to our PPFD times 60 seconds times 60 seconds in a minute, 60 minutes in an hour, 18 hours in a day. So if we take 60 times 18, we are going to get 64,800. And again, that is ultimately going to be divided by 1 million micromoles per mole. So we're yet again going to go through our cross multiplication and division. So in this case, if we go ahead and multiply both sides by 1 million, we are going to find that we have a target now of 18 million micromoles per meter squared per day. And that's going to be equal to PPFD times 64,800. We can then divide both sides by 64,800, and that is going to give us our final answer of PPFD is going to be equal to, if you're doing this with me, divided by 64,800. So our target light intensity should be 277.8 micromoles per meter squared per second. So I hope going through these calculations that you see how versatile and useful this can be. This is the kind of calculation that I call my back of the envelope calculation. If I'm working with a grower or working in the greenhouse, there are many times that I quickly need to do these conversions back and forth between PPFD and DLI to make sure that I'm giving my plants the appropriate amount of light, adjusting my supplemental lighting system accordingly. And so really important to know how to leverage this equation, and hopefully these examples have helped you in being able to do these calculations on your own.